Hi everyone, my name is Dr. Afaq, and in this video we are going to discuss the improved version of strength sensor that we did in the last video. If you remember, we discussed about a flexible strength sensor which used the conductive sensing material of glass roll and potassium chloride. If you remember, we discussed that there are still some parameters which are needed to be improved, and the research is all about providing some improvement in the previously published material, or if you have developed a sensor, of course there would be some features they are not as promising as they are needed in the prevalent applications. So in that case, it's quite important that we should improve. Some of the improvements that we incorporated, they are provided in this manuscript, and the title of this manuscript is Robust Fluidic Biocompatible Strength Sensor based on PEDOT, PSS and CNTs composite for human, wearable and high-end robotic applications. So of course we have targeted the same applications, but some applications have been introduced in this research article, and the sensing layer is changed, and due to this we have achieved some better results. So the journal name is Sensors and Materials, and that was published in 2020. So I think within few months we published after the acceptance of this manuscript. Anyway, so this is the research article. These are the authors, and let's just jump to the abstract of this article. You can see that we have used the composite of multi-wall carbon nanotube. They are highly conductive, and PEDOT PSS, that's also a conductive polymer. So we use a liquid type material, a composite of both materials, and that was used in the channel of this sensor. Overall, the structure of this sensor is similar to what we did in this paper, but there is difference in the approach, there is difference in the sensing material that we have used, and of course some applications have been introduced in it. So there are some factors like in the last article we could only stretch the sensor up to 100%, but in this article you can see that we could the sensor could be stretched up to 150%, and it still showed the remarkable sensitivity. And the gauge factor in the previous article, if it was quite less, so we managed to achieve up to 89.4 gauge factor. That means it's quite sensitive, and the hysteresis is of course a very prominent and decisive factor for the practical applications of your sensor, and in this article it is 1.56%. Of course the linearity is quite better result, and the sensor is waterproof, similar to what we did in previous work. And very interesting thing in this paper is that we have claimed that the sensor is biocompatible, and even our previous paper, the sensor we developed, that was also biocompatible, but we didn't prove its biocompatibility, because sometimes you use the process that is not biocompatible. Means the material that you're using, they are biocompatible, they are well known biocompatible materials, but maybe the fabrication process doesn't enable the whole process and the end result as biocompatible. So we have also proved that in this paper. So let's jump to the results, and you will see what we have done. The fabrication process, as I already told, that 2.5 half cycles were there. That's similar. In that we used blood coating for the fabrication of membrane. This is a mold that we 3D printed, and this is the ECOFLEX that we poured in it, and after it got cured we got this engraved channel, and then we blood coated the half cured membrane. After that the whole sensor was fabricated, and by the end we used this biocompatible sensing material using fluidic system to add in it, and then we added the conductor, means electrodes. So we had this universal testing machine that could be programmed using a simple Arduino development board, and you can stretch it even up to 80-90%, 800 to 900% strength. But this sensor we stretched up to 150%. Even we could do beyond 150%, but the sensor was not providing a consistent output. That's why we can say that up to 150% the sensor was providing a complete sensing response. So this is a basic characterization setup. We had LCR meter which was measuring the resistance, DC resistance, and the data was being logged into the computer. And this whole setup, the main part is stepper motor that was controlled using a microcontroller. So these are some real pictures of the stretching of sensor. You can see the black color because the PEDOT PSS and CNT, they have a dark color, and that's once you stretch it, you will see that the overall stretching goes with those cycles which are engraved in this sensor. And it's biocompatible as well as it's waterproof. If you put it into water, still it can be responsive, sensitive, and without no effect on its output. So this is the sensing mechanism. The very basic case, of course, once you stretch it, the length increases, the area a little bit decreases, and overall the resistance increases. But here you can see that PEDOT PSS and multi-wall carbon nanotube, they have a complex interconnected network, a conductive network, and as you increase the stretching, as you increase the length of the sensor by applying some stretching force, so what happens that carbon nanotubes, they go far from each other, and now the conductive network will get disturbed, and that will increase the resistance. So here you can see this is similar what we did in the previous work, and this is showing that why we introduced this structure, and this is Raman spectra. Then you can see the results and loading and unloading. This means that if you stretch the sensor up to 150%, then immediately release this sensor back to its original position, that's 0%. So you will see that both the results, they are quite consistent, and only the degree of hysteresis is 1.56%. And in the previous result, I think it was 4 point something percent. And this sensor was quite sensitive at even higher speeds. Means if you even stretch this at a speed of 10 Hertz, which is quite higher, then you can see the result is still quite significant and distinguishable. Then the sensor has good immunity to the temperature, that means up to 40 degrees centigrade, and reflects that you can use it onto your body as a wearable sensor, and your body temperature will not affect its performance. Similarly, we said that this is also a kind of waterproof sensor. So we checked it in a relative humidity of 100% in a closed chamber, and the resistance of this sensor was quite stable, and the resistance was nearly 3.56, which is its original resistance. And then this is the stability graph, that we kept the sensor at a stretching of 50%, and it's quite obvious that the sensor doesn't change its response because we don't stretch it further. And this is again the gauge factor, and at 150% stretching it goes up to 89. Here this is a comparison, and you can also watch my previous video. In that I have highlighted the importance of comparison table and why it's important. And this is our previous work in which we designed our first strength sensor, and that was based on glass roll and potassium chloride. So you can see the performance improvement. In the last work it was 100% strengthening, range was there. In our current work it is 150%. Similarly, the speed was 5 Hertz, but in this article it is 10 Hertz. And degree of hysteresis, yes, it is 4.23%, but in this work it is significantly decreased, and it is 1.56%. Gauge factor, in the previous work it was very low and quite unacceptable, because as far as robotic applications are concerned, you need a better sensitivity, and this addresses this issue. and similarly 1000 cycles were characterized, and linearity is almost same. And then these are few other results like cyclic response of the sensor, and then further study of stability that we stretched for multiple cycles of the sensor at the different stretching rates. And then these are first 10 cycles and last 10 cycles of this result, and the response time was 0.72 seconds and recovery was 0.9 seconds, which is quite acceptable for our practical applications. And this is the result of 3 samples that were developed, and this is quite interesting. You can see over here that these are confocal laser scanning microscopy Z-stack images. Actually we cultured the cells on the surface of this sensor, and up to 156 hours we checked the cell viability, and you can see that cells growth is quite prominent. And this proves that if you are using this sensor with your body, if it has got a physical contact with your body, that means it's risk free, it's environmental friendly, and you can use it without any risk. And these are some applications like finger bending, elbow bending, then water drinking ability, then squats. If you're doing gym, then we added this sensor on the knee joint and checked how it relates to your motion of your knee. And then we also used this in a frog limb that we custom 3D printed it. And I will also make a video on our frog robot very soon, and we use this sensor onto its limb, and we checked that at different degree actuation we could see a very distinguishable result of a sensor. And then this is the result that shows that if you apply the stretching force up to 10 Hertz, you will see that sensor also follows this response. In the conclusion, I can read it that we have designed an ultra flexible, highly stable and linear fluidic strain sensor using a biocompatible conductive composite based on PEDOT pieces and multi-wall CNTs, means carbon nanotube. The inherent elastic property of PEDOT PSN and excellent conductivity of multi-wall CNTs enable the sensor to attain a 2-order change electrical resistance under the maximum strain of 150%. All the quantitative data is available. The culturing of these cells, one of our bio members, she helped us to culture these cells, and it was quite good to design this sensor, and I was very happy when we used this sensor while placing it onto our body or using it in a robotic application. It was really nice to see its remarkable performance. So these are the references. I think that's it from my side, and we can discuss this paper in detail, and if you are interested in it, we can definitely discuss further ideas how we can still improve it. And that's it from my side. Thank you so much.